Welcome back to our IoT series. In this third lecture, we'll be looking into the world of sensing and actuation in IoT. So in this video, particularly, we'll be speaking about sensors. We'll look into what sensors are, what is the classification of sensors, what are the different types of sensors available, what are the key considerations that we should know, and how deviations can affect the sensor's performance. And we'll also look into essential characteristics which are very important while designing or selecting sensors to create IoT solutions. So let's get started. Firstly, we'll understand what sensing and actuation is. So sensing is a crucial aspect of IoT applications as it is the first step in operations. Whereas when we come to actuation, it forms the first step in IoT, it forms the final step in IoT deployment and completes the process after sensing. So both sensing and actuation rely on the principle of transduction, which involves converting energy from one form to another form. So transducers, from transduction we come across transducers. Transducers are the devices that help in energy conversion. That is, it could be from electrical to mechanical or mechanical to electrical or chemical, vice versa. Both sensors and actuators are types of transducers. Let's consider an example, that is public announcement system. In this, anyone in the suppose if I speak on the mic, so the sound waves are converted to electrical signals, right? Through mic, the sound waves are converted to electrical signals. So from this we have amplifier which amplifies and processes the signals, and from there it goes to the speaker. In speaker is an actuator here which will convert the electrical signal back to sound waves. So here from sound it got converted to electrical and it traveled, and from electrical it got converted to sound. So this conversion is happening through transducer. So this was all about the introduction of sensing and actuation in IoT. Let's look into the differences here. So let's look into the differences one by one. Understanding the definition: converts energy from one form to another form. Whereas speaking of sensors, it converts energy of various forms, that is from environment, it converts it to electrical signals. Coming to actuators, it converts the electrical signals to various forms of energy depending on the output, whatever is required. Okay. Speaking of domain, transducers can be used to represent sensors as well as actuators, whereas sensors are called as input transducers because it will convert the environment data or environment factors into the electrical signals, right? So it is in the starting initial part of the IoT process. And coming to actuators, it is also called as output transducers. What is the function of transducer? It can work as sensor or actuator, or it can work as sensor or actuator but cannot work as both simultaneously. Whereas sensors convert the environmental stimuli into electrical signals, and actuators are used for converting signals to proportional mechanical or electrical outputs. Looking at examples, any sensor or actuator can be called as transducer. Whereas examples of sensors include humidity sensor, temperature sensor, anemometer, that is to measure the flow velocity, manometer to measure fluid pressure, accelerometer to measure the acceleration of body, gas sensors to measure the concentration of specific gas, or and many others. Whereas when we come to actuators, examples are motors to convert electrical to rotary, and we have force heads which impose force, pumps which convert rotary motion of shafts into either pressure or fluid velocity. So in exam, this particular question is very important. It will be asked for maybe 10 marks. We have to specify all these points and write it properly. Moving on further, the next topic which we have or will be discussing in detail is sensors. So sensors are the devices that detect and respond to change in the environment. Yeah. So looking at the definition here, it converts various forms of energy, that is from environmental stimuli into electrical signals. What is environmental stimuli? At times we come across these terms: environmental stimuli, physical phenomena, and environmental factors. All these three are same. So environmental factors which could be measured are humidity, temperature, flow velocity, and pressure. Right. Moving further, sensors only detect the properties they are assigned for. That is, they are very specific. Sensors only detect, like if it is a temperature sensor, it will measure only temperature. It won't detect light or pressure, right? and they ignore other properties. Yes, sensors are non-intrusive. Sensors don't affect the property they measure. Like for example, if I'm measuring the temperature, the actual temperature of that particular liquid or solid or that gas won't be fluctuated, or it won't be altered, right? So it is not intrusive. Moving on further, here we have a outline of simple sensing operation. So we'll look into that one by one. So in this, the first step which we have here is environment. In environment, the event is fire. That is the surrounding where the sensor operator is called operates is called environment. So environment like a fire can cause increase in temperature, right? So when the temperature increases, we have sensing. That is, we are making use of temperature sensor here. So as there is fire in the environment, and in the second step we have sensing, that is we are making use of temperature sensor which continuously monitors the environment, and it detects if there are any changes. So because of fire, when there is increase in temperature, it detects the temperature firstly, and then converts it into electrical signals. Then we have third step, that is processing. In processing we are making use of sensor node. So the sensor sends electrical signal to a sensor node which further processes the information. So sensor nodes interprets the data and determines that fire has occurred in the environment. So after this we have monitoring. Fourth step is monitoring here. Monitoring can be done in the desktop or mobile or any interface. Okay. So after processing, the information is sent to a remote desktop or a remote monitor. So by this monitor, we can understand that there is fire in this particular house or this particular room. Okay. So this helps us to take appropriate action. So this is how the entire sensor operation works. So initially, let me summarize it up. Initially, in a particular environment, there was fire detected. This fire increased the temperature. Because the temperature has increased, the sensing operation took place. That is, it detected the temperature rise and converted it into electrical signals. From there, it was further sent to processing. The processing happened in sensor node, where further processing of information took place. Then from there, it went on to the desktop or monitoring platform, where the end person will detect that or will understand that there is fire in this particular place and will take appropriate action. So this was all about the simple sensor operation. Moving on further, we have different types of commercially available sensors which are used for IoT sensing operations. We have a camera sensor that is used to detect any object or image. Then we have color sensor used to detect color, compass and barometer, current sensor, digital temperature and humidity sensor, flame sensor to detect if there are any flames, gas sensor to detect if there's any gas, infrared sensor, that is it is also called as proximity sensor. Then we have rainfall sensor or water detection sensor. Then we have ultrasonic distance measurement sensor in order to measure the distance. So these are commercially available. We have almost made use of we must have made use of these in our IoT projects, right? Moving on further, we'll look into the classification of sensors. So depending on different criteria, the sensor is classified as power requirements, property to be measured, and sensor outputs. Firstly, we'll start with power requirements. Power requirements is further classified into active sensors and passive sensors. So active sensors means they do not need any external power source. So active sensors directly convert the external stimuli from the environment into output signals. So direct conversion of environment stimuli to signals. So example here could be photodiode. So we know photodiode converts the light to electrical signals. This conversion happens directly. We are not providing any power supply there, right? Photodiode convert light to electric signals. This was about active sensors. Looking at passive sensors now, as we understand by the definition, power requirements on one side, power was not required. That is called as active sensors. So opposite to that, it will be power is required here in case of passive sensors. So passive sensors require power source, and along with that, the output whatever we obtain is altered based on the sensor's inherent properties. Moving on further, let's write the example. Example could be alcohol detector or alcohol thermometer. So this works only when we put cells in the alcohol detector device, right? So it requires power supply. So this was about power requirements. Further moving on, we have sensor output. So sensors generate different types of output. So influencing how they integrate with digital or analog systems. So we come up with analog sensors and digital sensors. Analog sensors produce continuous output signals or voltages proportional to the measured quantity. So let me write it down here. It produces continuous output signals or voltage proportional to measured quantity. Whereas when we speak of digital sensors, it produces discrete signals that it gives discrete signals. Discrete signals means it will be in zeros or ones, that is binary. The logic here is in binary. Okay. So analog signals are suitable for measuring continuous physical quantities. Continuous physical quantities, which include the temperature, time, speed, pressure. All these are continuously varying, right? So analog signals are used in such time. Example is thermocouple. So thermocouple measures the continuous temperature of water heater. When we come to digital sensors, output may be a single bit or multiple bits transmitted. Output is serially transmitted or parallelly transmitted. Example could be digital thermometer. So this will give discrete temperature readings, whereas in case of thermocouple, it gives continuous temperature of water heater in water heater. So we are done with the sensor outputs. Moving further, we have property to be measured. So sensors also vary based on the type of environment property in which we are measuring. So firstly, we have the scalar sensors. Scalar sensors will measure scalar qualities. Sorry, scalar quantities. That is only magnitude. Whereas when we come to vector, here vector sensors, here it is vector quantities, that is magnitude plus direction. So output is a signal or voltage proportional to magnitude here. Output is proportional to magnitude. Here output is both dependent on the magnitude and direction. Here example, let's write thermometer. So thermometer measures the temperature, but it is not affected by the orientation, right? Whereas when we speak of vector sensors, we can take example of electronic gyroscope, which measures the orientation along all the three axes, and this is used in aircrafts, right? So we are done with the sensor classification. Moving on further, here we have the diagram. So this diagram is again important. It could be asked in exam. The functional block of functional block of typical sensor node in IoT. So here we have several components. Let's discuss them one by one. So the first one which we have is sensor here, right? So the purpose of sensor is to detect and measure the environmental conditions and convert them into electrical signals. Example could be a light sensor or temperature sensor like a thermocouple or thermocouple, which is used to measure the temperature changes. There could be a pressure sensor like a barometer to detect atmospheric or fluid pressure. We have chemical sensor, that is the gas sensor, or speed sensor, position sensor, force sensor, and light sensors. So here analog to digital conversion is taking place. Further, we have processor unit. Processor unit comprises uh, processor unit will first take the signals from the sensor, and there are embedded programs here. So it runs embedded programs and manages the communication between the sensor and the other components. Okay, and like it also takes care about data filtering and conversion, decision making, and all the other features. Examples here are we must have known about Arduino board, right? Arduino is microcontroller, or we can make use of Raspberry Pi, which is a microprocessor. This is advanced. This is used in advanced IoT systems for like complex data processing and different complex tasks. Then we have actuator here. Actuator is optional. Okay, at times there may not be actuator in sensor node. Okay, actuator converts the processed electrical signals into physical actions or whatever the output is expected. So in some IoT systems, actuator respond to sensor data by performing tasks such as moving a particular uh, any part, or if there is any alarm to be turned on, that could be done, or in order to turn the sprinkler on, that could be done. Examples here are electrical motors, in case of electrical, it could be electrical motors which convert electrical signals to mechanical motion. So these are used in robots or in order to open the door and all. Speaking of hydraulic, we can make use of hydraulic power to open the doors, or put extra pressure and all. Mechanical or uh, pneumatic. Actuators types we have pneumatic, hydraulic, electrical, and mechanical. Electrical means to convert electrical signals to mechanical motion. So this could be used to like open the doors, airport doors, or metro doors. Yeah, right. Then we have hydraulic. Hydraulic is depending on the liquid pressure, do a particular action. Electrical is through electrical signals, and yeah, pneumatic actuators are used in air powered systems in order to move any parts. Then we have the radio unit. Radio unit will handle wireless communication. So this will handle the wireless communication between the sensor node and other nodes, or to the server directly, which will happen through radio node. Okay, so here we have Wi-Fi. Wi-Fi uses high-speed communication. It can be used in homes. Then we have Bluetooth. Bluetooth is a short-range wireless communication. Zigbee. Zigbee is low-power wireless protocol, which is used in smart home automation and all. Then we have LoRa, that is long-range, ideal for long-range distance communication. Then we have RFID and NFC. These are used in metro cards, right, or the contactless payments, tapping our ATM. Then we have Z Wave and 3G, 4G, 5G cellular based communication. Moving on further, the last part which we have is this part, that is the power unit. So power unit provides energy for the sensors to work. So sensors will require power, right, in order to work. This could be batteries. We can add batteries or provide electrical supply, and so on. So here it could be AC to DC converters are used here, or the power could be in DC or it could be in AC, right? And that's it. We have covered all the important components of functional blocks of typical sensor node in IoT. Moving on further, we'll look into the sensor characteristics. Sensors are defined by their ability to, in order to detect the physical phenomena and convert them into measurable signals. So, speaking of the characteristics, we need to look into three main characteristics here. Let me write it down here. The first one is resolution. Second one is accuracy, and third one is the precision. Now you might think all these three are similar when we speak in layman terms, right? But then no, when we are writing an exam or attending any interviews, answering this, we have to be very careful. Okay, so let us write down these points, these characteristics one by one. So firstly, we have sensor resolution. So sensor resolution refers to the smallest detectable change in the quantity being measured by the sensor. So it is the smallest measurable change. which could be detected by the sensor. So we can say that higher the resolution, finer would be the details, right? Higher the resolution, finer would be the details, and from these details it will be further helpful for us to take all the required actions. For digital sensors, the resolution is the smallest difference in the digital output that sensor can represent. Let me write it down. In case of digital sensors, they are the smallest, resolution is smallest difference in the digital output that sensor can represent. So resolution is very important. So the higher the resolution, it can help us to detect even the tiniest changes while measuring. So it will provide us detailed provide detailed data. So let us consider example of two temperature sensors. So temperature sensor A can detect a temperature change of 0.5 degree Celsius increments. And whereas when it comes to sensor B, it can detect change as small as 0.25 degree Celsius increment. Now you tell me, out of these two, which one will have higher resolution? We can say that sensor B has higher resolution. So as sensor B can detect smallest temperature variations, we can say that sensor B will capture finer details when compared to sensor A. Right. So this is what sensor resolution speaks of. Moving further, we are done with resolution. Now we'll look into sensor accuracy. So in sensor accuracy, understanding the definition, accuracy means the ability of sensor to measure the actual value. Okay. So measuring the actual value and checking how close it is to the possible actual value. So it reflects on how close the sensor readings are to the actual measurement. Sensor readings, how close to actual measurements. So accuracy is very important. Higher the accuracy, we can say that the sensor's output is true to the real world value. Higher accuracy, we can say that the sensor value is true to the real world value, and this also minimizes the error. It also speaks of minimizing the error while measurement. Now we look into the example of sensor accuracy. So suppose a weighing scale or weight sensor measures an object to be 100 kgs. Okay. Now the sensor shows reading of 99.98. This means sensor has 99.98% of accuracy. That is, it is very close to the measured value, right? That is 100 kgs. Here we can say that the error is only 0.02%, which this entire scenario says that it is having high accuracy. Okay, moving on further, our next characteristic we have is sensor precision. So firstly, we have to understand that precision means repeatability. That is, when we are measuring same product, sorry, same object under same conditions or environment for multiple number of times, and if we get same output, then we can say that our sensor is 100% precise. So a high precise sensor will give same value every time it is measured, and it need not be accurate, perfectly accurate, but similar nearby values if we are getting, then we can say that it is high, it is having high precision. Okay, let us look into an example. Let me consider the same weight sensor which we used here above. It was the weight was 100 kgs, right? So let me take the first reading. I got 98.88. The second reading I got 100.21, and the third reading I got 100.01. So if we see these three readings, it shows significant variation, indicating that sensor has low precision. So if the values were very close, suppose if I had taken 100, if the first reading was 99.99, second reading was 100.01, third reading was 100.001, then we can say that it is having high precision. But this is a ideal situation, right? There will be error, there will be like problems will occur, or the deviation will be there definitely. So this was all about the sensor precision. Here we have discussed all three characteristics. Moving on further, we'll now look into the different types of sensor deviations and errors. So sensor deviations refers to errors or inaccuracies in sensor measurements. So these arise due to different factors. It could be the environment conditions, or maybe our sensor is not designed properly, or while sending the data there might be some error, or while sending the signals there might be some error. So these deviations play a very important or a sensitive role while measuring the healthcare or industrial monitoring or any other serious application. Okay, let's look into the let's look into each type of deviation and error with definitions. Reading out all the errors once, we have hysteresis, full scale range, and truncation. We have sensitivity error, non-linearity, offset or bias, drift, environmental sensitivity, noise, aliasing, and quantization. So let's start from the first one, that is we have full scale range and truncation. So the full scale range of sensor tells the range between its minimum and maximum measurable values. Range means it is between minimum and maximum measurable values. So if a sensor measures anything or the value which is beyond the range, then it is said to be truncated. The output is said to be truncated. Truncated means output is not in range or the limit. For example, a temperature sensor has the range of minus 40 degrees Celsius to 100 degrees Celsius, and if I have measured and I got 120 degrees Celsius, it is wrong, right? So if the sensor is exposed to 120 degrees Celsius, it will go up to 100 degrees Celsius and stop due to truncation. That is, it is exceeding the limit, right? So this was about full scale range and truncation. Moving on further, second we have is sensitivity error. So sensitivity error occurs when actual sensitivity of the sensor differs from the specified sensitivity. Actual sensitivity differs from specified sensitivity. We can say that in world, any IoT device, any object for that matter will have sensitivity error. There is no 100% proper error free object available. So there will be some sensitivity specified. If the error is changing with the if the actual value which we have obtained is differing from the specified sensitivity, it is called as sensitivity error. So this happens when there is fabrication issues or fabrication defects or calibration issues. For example, let's take a pressure sensor. So this pressure sensor is supposed to detect 1 unit of pressure per 10 Pascal. But due to a sensitivity error, it may detect 1 unit for only 9 Pascal. Here we can say that this is causing inaccuracies in the measurements. So this was about sensitivity error. Next we have is offset or bias. Offset error or called as bias. So offset error occurs when sensor consistently adds or subtracts a constant value from actual measurement. Let me write it down here. Occurs when sensor consistently adds or subtracts a constant value, or it is also called as offset value, from actual measurement. So the sensor output is either always higher or lower than the lower than the real value. Okay, the output is either higher or lower than the fixed real value, and this fluctuation also is between a consistent range. This is called as offset error. Looking at an example, we'll take a temperature sensor that always reads plus 11 degrees Celsius more than actual temperature. So for a true temperature, if the temperature is 0 degrees Celsius, it will report 11 degrees Celsius. That is, we can say that there is offset error of plus 11 degree Celsius. Moving on further, called non-linearity error. So by definition, we can say non-linearity error will occur when the output does not follow a straight line in relation to the input. We can write when output does not follow straight line relation with input, non-linearity error occurs. So this deviation from the expected linear behavior results in varying degrees of inaccuracy. Especially, it gives out extreme values. For example, if we take a pressure sensor, so this pressure sensor is expected to output a straight linear curve as pressure increases. Expected to give straight linear curve as pressure increases. But when the output varies irregularly, this was expected, but then we are getting this. So in this case, we can say that incorrect readings have been taken, and fluctuation is happening at output side. So these two things will arise when we have non-linearity error occurring. Now we'll look into our next error. Our next error is drift. So drift refers to the gradual deviation of sensors readings over time. So drift is caused by physical changes that are happening in the sensor components or sensor materials. So drift will happen slowly. It could take months together or years together. So example is humidity sensor. Humidity sensor, when you install at the first time, it will give 100% accuracy. But after 10 years, because it was extensively used, the sensing property of this humidity error has been deteriorated. In that case, there will be 5% lower humidity reading. In such situations, we can say that drift has occurred. Okay, moving on further, we have noise. So noise refers to the random variation in sensor's output that occurs over time, that occurs over time. And the reasons here could be because of electrical interference, or it could be temperature fluctuations, or any other environmental factors. Looking at an example, we'll take a digital thermometer. Okay, so the actual reading is 25 degrees Celsius, but then it will fluctuate between 24.9 degrees or 25.01 degrees. This error is happening because of electrical noise or electrical interference. This is called as noise. Moving on further, we have hysteresis error. Hysteresis error occurs when current sensor output depends on previous input values rather than taking or considering its current input values. It is commonly seen in analog and magnetic materials. So taking an example, well, let's take a magnetic sensor which measures 10 units for a specific input. Now that I have varied the input, I have increased the input value, but still I will get 10 unit reading only. In this case, we can say that hysteresis error has occurred. Next we have is quantization error. Quantization error occurs in digital sensors when analog sensors is approximated during conversion to digital value. So the difference between true signal to the digital signal approximation is called as quantization error. Let's take an example, digital light signal. So the light had actual value of 45.6 units, but then during the conversion, after the conversion, we got digital values as 50 units. Here it was 45.6, here we have got 50. So we can say that quantization error has occurred. Next we have is aliasing error. Aliasing error occurs when sampling rate of sensor is too low compared to the frequency of signal which is being measured. So it causes different signals to overlap and appear as one. Aliasing means overlapping or using the same name, right? Thus, distortion of data is happening here. Let's consider a signal which is used to measure vibrations of motor. So the motor is running at 500 hertz. Okay, but the sampling rate here is very low compared to the frequency. Here it was 500, but then the rate which we have here is 250 hertz. So it is obvious that the sensor will give incorrect data. So by having the incorrect data, we can say that aliasing error is occurring. Our last error which we have here is environmental sensitivity. Environmental sensitivity is the deviation in output based on environment factors. There could be different environment factors like the temperature we have discussed in the starting, right? Humidity. There could be electromagnetic interference and so on. So this deviation which occurs in output is called as environmental sensitivity. Let us consider a semiconductor gas sensor. So semiconductor gas sensor readings vary depending on the temperature. If it is normal temperature, we might get some value. Upon an ambient temperature or a varied temperature, we'll get a different value. Though the same gas is being measured, the same gas is being sensed, but then still there is fluctuation in the value that is happening because of environmental sensitivity. So here we come to a conclusion of all the different errors. Next, moving on further, we'll discuss about sensing types. So sensing types are basically classified into four types depending on the nature of environment and the sensor used. Those four types are, firstly we have scalar, then we have multimedia, then we have virtual, and the last one we have is hybrid, combination of multimedia and scalar. So let's start from scalar. Okay. So scalar sensing means involving measuring values that do not have any direction, only scalar values. Measuring only scalar values, that is only magnitude. Here we are looking only the magnitude which changes over time. So example could be monitoring temperature or humidity or light sensitivity. All these are magnitudes only, there is no direction involved here, and these are varying with respect to time, right? So for example, a temperature sensor in fire alarm measures ambient temperature over time to detect if there is any rise in fire, uh, uh, that is telling if there is any fire in any apartment or building or not. This was about scalar sensing. Next we have multimedia sensing. So multimedia sensing involves multiple properties. It could be multiple properties both with respect to time and space. So they are vector quantities which are measured here. For example, let's take a camera. Okay, camera in a surveillance system that senses videos which involve, which take care of the 3D changes, right? Which will consider 3D values in all the axes, x, y, z axes. Similarly, we can speak of microphone. So microphone captures sound which also changes with time and direction. Next, we have hybrid sensing. In hybrid sensing, it is a combination of scalar and multimedia sensing. So we are making use of different types of or combination of these two sensors in order to get more comprehensive data. We make use of hybrid sensing. In example could be in agriculture, we make use of soil moisture and temperature sensors, which can be combined with cameras to monitor plant health. So from cameras we can monitor the plant health, and we can also look into the what is the color of the leaf and moisture levels and all of that. All this can happen by combining the scalar quantities here as well as the multimedia sensing quantities here. Next we have is the virtual sensing. In virtual sensing, we take data from existing physical sensors, and then which are stored like to infer data from locations where there are no sensors. This is mostly happening through extrapolation. So let me write it down here. We take data from physical sensors to infer data for locations or situations where there are no sensors. So an example for this could be, suppose if I want to measure or sense something on Mars. So each and every time I can't go to Mars, right? Whereas uh, similar properties which could be found on Earth or with similar elements or atmosphere, if I measure it here and take that data and further perform various extrapolation activities, it can be termed as virtual sensing. So another example could be if a farmer A has sensors for soil moisture and temperature, neighboring farmer B can use the extrapolated data from A and check about what is the soil level and what are the temperatures without adding extra sensors in his land. So farmer A has moisture sensor and temperature sensor here. So from the data which is obtained, farmer B is using this data. He's not actually installing the sensors here. He's virtually using the extrapolated data and then implying or doing necessary changes in his particular farm. So this was about the sensing types. Moving on further, discussing about sensing considerations. So sensing considerations means while we are deploying a IoT sensor in a particular project or a particular purpose, we have to make sure that we achieve efficiency, reliability, and practicality. In order to get all these, the range should be considered, accuracy and precision should be considered, energy consumption should be considered, and the device size is also important. Let's start with the first consideration, that is sensing range. So sensing range means the area within which our sensor can detect any changes or any events occurring. For example, if we take a IR sensor, it can detect up to few meters. For example, a proximity sensor, it can detect only 1 2 meter. If there is any object present, it will detect and tell. Coming to camera based sensor, if it is used for surveillance, it may have long range. For it could be hundreds of meters. It can be like we can see these things in parking lots and all, right? So in order to establish the sensing range, we have two options: either to fix our sensor in a particular area, and thereby we'll be getting the data, right? We'll be getting the information. Or it could be dynamic coverage, that is, camera based sensors are also installed in drones, right? During on the border, if there's any threat, we can make use of drones, and thereby we are dynamically moving the area or the region, right? Thereby the data would be sensed accordingly. Next we have is accuracy and precision. So accuracy is how close our sensor measurement is to the actual value, measured to actual value. And precision is consistency, while we measure the same input for same environment over multiple times. So the required accuracy and precision depends on the application. For consumer grade sensors, it may have lower accuracy, but they are cheaper. While in case of industrial grade sensors, it should have higher accuracy. At the same time, the cost will also be higher. In case of consumer grade sensors, accuracy and precision is low, so cost is also low. Whereas when we speak of industrial sensors, the accuracy has to be high, thereby the cost will also be high. So this is again one of the characteristic. Example could be a normal standard temperature sensor. If I take, it comes under the consumer grade sensor, whereas if I take industrial temperature sensor, so in standard temperature which is used in home thermostats, it may have accuracy of plus minus 0.1 degree or 2 degrees, whereas when it comes to industrial temperature, even 0.01 fluctuation or the accuracy of 0.01 is also can pose a lot of threat, right? It is not acceptable there, because we are dealing with large chunk of data and huge investment. Next we have is energy consumption. So energy efficiency determines how long a sensor can operate before we need to charge it again or put the battery again. So energy consumption directly is proportional to the cost and feasibility of deployment. If I consider a particular device which requires to be charged every 24 hours once, it is not feasible for me, right? So in remote or hard access locations, sensors must occupy, or sensors must consume less energy, because if it is consuming fastly, then maintenance will also increase, right? Examples could be environmental monitoring system on glaciers. So if I install environmental monitoring system on glaciers, I cannot go there every now and then, right? So once a battery is put or once it is charged, it has to go on for years and years. Such sensors should be used. Whereas the wearable fitness trackers, I can charge it every day because I use it personally. It is with me all the time, right? So this was about energy consumption. Let me write down few points here. It determines how long sensor can operate without the need to charge or supply energy. So examples, let me write down here. Environmental monitoring sensor on glaciers, and on the other hand I have the fitness trackers. Here the battery should come for years together, whereas when I speak of fitness trackers, I can charge it any time. So depending on application, particular device need to be selected. Moving on further, we have device size. So device size plays a very important role, right? The size of sensor affects its practicality, especially in applications where it has to be very small. Size matters a lot. So small sensors are mostly desirable because they can cause less interference in daily activities and consume less energy. For example, the wearable sensors in fitness trackers need to be very small. So if I have my watch to the size of my mobile, can I wear it on my hand? No, it is not possible, right? And when it comes to a large human activity detector, it has to be of huge size, the metal detectors. It can be of a human's 6 feet, 7 feet accordingly. So depending on application, the device size also matters a lot. So it speaks about the practicality and cost effectiveness. So again, depending on the application, size small or size large is preferred for the sensors. The sensors which should be of smaller size, example is wearable devices. Whereas when it comes to large sized sensors, it could be metal detectors. So minimization and effective design are very important when it comes to designing such complex or modern IoT devices. So here we come to an end of the considerations. So we have discussed all the sensing considerations, and then we have covered the sensing types. We have also looked about the errors which occur, the sensor deviations and sensor errors, and along with that we have also spoken about the sensor characteristics. We have seen the functional block diagram of sensor node, and then we have spoken about sensor classification and a simple sensor operation and sensors and the basic introduction. So this was all about the lecture 3. The actuators topic will be covered in the next lecture. Stay tuned. If you have any doubts in this video, do let me know and subscribe to my channel.